Hello and welcome to video 5. In this video we'll be looking at rounding, significant figures, truncation and limits. So first of all we have rounding, and when we round, say we have 2.3764, and if we round to 3 decimal places, well, we go in 3 decimal places in, and we can draw our imaginary line here. And we look at the number after the line. If the number after the line is 0, 1, 2, 3 or 4, then we leave this number, the number before the line, as it is. And this is called rounding down. And if it's a 5, 6, 7, 8 or 9, we round up and we increase this number by 1. Well, in this case it's a 4, so we just leave it as 2.376 to 3 decimal places. If we were to round to 1 decimal place here, well, we have a 7 after the dotted line. 7 is a 5, 6, 7, 8 or 9, and that means we round up. So it's 2.4, not 2.3, to 1 decimal place. It's usually preferable to use this bit here in brackets 1 dp or 2 dp, just to make sure the examiner knows how much you've rounded to. Sometimes you need to round to a number of significant figures, so say we had 0.000637 and we wanted to round to 1 significant figure. Well, we start on the left and we keep going throughout the number until we get to the first number that matters. All these zeros here don't matter. They don't give us any value. The first number that matters is the 6. So we draw our imaginary line after the first significant figure and we look at the next number. Like rounding, if it's 0, 1, 2, 3 or 4, we round down, so we just keep this as it is. And if it's a 5, 6, 7, 8 or 9, then we round up, so this will become 0.0007 should the next number be 5 or above. In this case we have a 3, which means we round down, so therefore we have 0.0006 to 1 significant figure, to 1 SF. If we were to round to 3 significant figures, well, it would just be the same thing because we have no more values after here. If we were to round to 2 significant figures, we would put our dotted line here and we'd look at the 7. The 7 means we round up, so we'd have 0.00064 to 2 significant figures. Now sometimes you may get numbers such as 2.00003, and when rounding to a number of significant figures, well, if we were to round to 1 significant figure, we'd just have the 2 here. If we were to round to 2 significant figures, these zeros do matter because they're after the 2. So this number to 2 significant figures would just be 2.0. We would not go all the way to the 3. That wouldn't be significant figures. If we went all the way to the 3, we'd be rounding to 1, 2, 3, 4, 5, 6 significant figures. Now finally we have some cases where we have, say, 1.00302. If we were to round to 4 significant figures, well, we look at 1, 2, 3, 4. 1 is the first significant figure, so 1, 2, 3, 4, and we put our imaginary line here. And we have a 0, so we round down, so 1.003 to 4 significant figures. If we were to round to 5 significant figures, we put our imaginary line here, and the 2 means we round down again, so it's 1.0030 to 5 significant figures. Even though this last 0 doesn't seem like it matters, it does matter, because if we don't put the extra 0, it means we're rounding to 4 significant figures, not 5. Finally, we have truncation. Truncation just means we're cutting the number at a certain point. For example, if we had 17.3427 and we wanted to truncate this number at 2 decimal places, well, we just draw a line there, we put 17.34. regardless of the number after. If we were to truncate 8.36 to one decimal place, we draw a line there, it's just 8.3 to one decimal place. And this 6 has no effect on rounding up. We're just truncating. Truncating means we're cutting off the number. If we have another example, such as 17.829, and we were to say that this was rounded to 3 decimal places, or this was rounded to 5 significant figures, well, what could it have been? Well, it could have been 17.8295. Could it have been that? Well, no, because if we were to round to 3 decimal places, this would become 17.830. So that wouldn't work. But if we looked at 17.8285 and we drew a line there, well, that would round to 17.829. However, anything lower than this, so such as 17.8284, would not round to 17.829. It would round to 17.828. Anything less than this, however, anything less than this number here, would round to 17.829, just because if you draw it on a number line, again, we have 17.829, we have 17.8295, and 17.8285. We know that this would round, and this wouldn't round, but anything less than this number would round. And so this is some notation here. If we forget the ticks and crosses, this is a number line. We're looking at the interval, the error interval we call it, which would round to 17.829. And we know that where we have a circle that's filled in, we're taking that value, we're including that value, and where we have a circle that's not filled in, we're not including that value. So we're saying that anything on this number line, anything specified by this notation, would round to 17.829. And you'd get questions with this, such as if you have a cuboid and we have lengths 4.5, 1.5 and 1.7, and they're all rounded to one decimal place, then what is the minimum volume and what is the maximum volume that this cuboid could have? Well, the minimum volume, V min, is going to be the minimum length, minimum width times the minimum height. And that would be 1.65 times 1.45 times 4.45. And the maximum volume, V max, would be the maximum of each side length multiplied all together. So that would be 1.75 times 1.55 times 4.55. However, errors is slightly different with truncation. Say we have the number 2.63 and we were told that was truncated, not rounded to 2 decimal places. Well, we know that it has to be the 2.631, 2, 3, 4, all the way to 9, and 0 in fact as well. And we know it can't be 2.625, for example, because we're not rounding, we're just truncating. So the error for this, it's either 0, it's between 0 and 9 after the 2.63. So we know that it is x is more than or equal to 2.630. However, x is less than 2.640, and therefore we can write 2.63 is less than or equal to x is less than 2.64. And that would be the error interval for such a truncation that we have here. Now going back to an example about upper and lower bounds. So if we have a cuboid, very simple, but if we have a cuboid and we have the length is equal to 3.4 truncated to 1 decimal place, And if we have the width equals 2.67 rounded to 2 decimal places, and if we have the height is 1.34 to 3 significant figures, and we were asked to calculate the upper and lower bounds for the volume of this cuboid. Well, we know that the minimum length is 3.40 because it's been truncated. The maximum length, however, is 3.50. I know we don't include this number, but for the purpose of the upper bound, we will just use 3.50. We know that 3.50 couldn't have possibly been the value because we know that 3.40 is less than or equal to length is less than 3.50, and we know the minimum width is, well, it's 2.665, and the maximum width is 2.675. Now the minimum height is 1.335 and the maximum height is 1.345, and so now we can say here that the minimum volume, V min, is equal to the minimum length times the minimum width times the minimum height, and you should write that down. So L min times W min times H min, and that gives 3.40 times 2.665 times 1.335, and that gives 12.096435, and we can round that to, usually you'd look at the same number of decimal places or significant figures in the question, so we should, I'm going to give it to 2 decimal places, so 0.9, well, we draw our imaginary line here. Don't draw this imaginary line in exams. 6 means we round up, so we'll have to round to 12.10 centimeters cubed. And V max, I don't have space to write it, but L max times W max times H max, which is 3.50 times 2.675 times 1.345, which gives 12.5925625, which we'll round to 12.60 centimeters cubed. And I say centimeters cubed, I should have specified here in the question that this is centimeters, centimeters, centimeters. And now we know V min is our lower bound and V max is our upper bound. Now occasionally you may be asked to calculate the percentage error posed by the lower bound and the upper bound. Well, we have our lower bound is 12.10 and our upper bound is 12.60, and we can work out our volume using the numbers they've provided, which is 3.4 times 2.67 times 1.34, which gives 12.16452, which will round to 12.16 centimeters cubed. If we were asked to calculate the percentage error posed by the lower and upper bound, we subtract the lower bound from the upper bound, so 12.60 minus 12.10 equals 0.5, and 0.5 divided by 12.16 times 100 to make it a percentage is 4.11%, and that's to 2 decimal places. Thank you very much for watching. Please subscribe for more maths videos.